Okay, so we're going to have a look at the energy that's stored on a capacitor. We already know something about the charge stored on a capacitor. We know that the charge is equal to C times V, where V is the potential difference across the plates once the capacitor is charged up. So how are we going to find out how much energy is being stored? Well, when energy is transformed from one form to another, we know that work is done, and we know that electrical work done is given by, do you remember? Queen Victoria, QV. Electrical work done is Q times V. So when charge moves through a potential difference of V, work done of Q times V is done on it. So let's have a look at a capacitor and see how this works. Well, if I first of all charge it up, I might connect it to a power supply with an EMF of V. And what that's going to do is pull electrons off that plate and push them onto that plate. And then I can disconnect the power supply. And the situation I'm going to be left with is a capacitor which is charged with plus Q coulombs on that plate, minus Q coulombs on that plate. And we say it's charged to a charge of Q. And we know that at that moment there will be a potential difference between the plates. And so I could put a voltmeter here. And at that moment in time it would read whatever the EMF of the power supply was. So let's say that was big V, capital V. Okay, great. So, well, at first glance it looks like, hey, well, we've kind of got the answer, that the energy stored is just going to be Q times whatever the potential difference between the plates is. Unfortunately, it's not quite that simple. Well, let's see if we can figure out what's going on. So, well, we've got energy stored on this capacitor that we can sense because there's this charge which is in its potential energy. The charge wants to repel itself, the electrons want to escape this kind of repulsion that they're involved in and get back to where they were happily at the beginning. Well, the only way they can do that is if we allow that energy to be released. So let's do that. Let's just put a little circuit with some resistor, and as soon as we connect that, then that will allow the electrons to flow back round, and the energy stored will be released. Let's look at a graph, and we know what a graph of charge against potential difference looks like for a capacitor because we've been studying that, and of course it's just Q equals CV, so it's a straight line graph. And now this is very helpful in enabling us to understand how much energy is released and therefore how much energy was stored on the capacitor. Because initially, as soon as we connect that circuit and allow that energy to start being released, well, we can see that the very first charge the very first little bit of charge is going to fly back around the circuit, and it's going to move through a potential difference of, so if I just take that little chunk of charge there, then it's going to move through a potential difference of about V, and the maximum potential difference that our capacitor was charged to. So in other words, here my value of potential difference is about V, it's slightly less at the left hand side. And let's say that I've got here my little amount of charge, let's just call it delta Q, there. Well, we can see that the area of that kind of little strip there is going to be the energy released, or the work done on the charge, the electrical work done, as that charge moves back around the circuit. Okay, and we can see that that value is going to be, if I just label it, is going to be QV, so it's going to be delta Q times V. But of course, the thing is that the potential difference is dropping. This is going to drop steadily down to zero, the potential difference across the plates, as the charge is redistributing itself. Exactly how that happens is the topic of a future video, but for now, let's just look at another position. Let's look, say, halfway down. Well, the little bit of charge, the little sort of chunk of charge which flows off approximately when there's only half the charge remains on the capacitor, well, then obviously the potential difference now between the plates is going to be much smaller. I mean, to be precise, halfway is going to be about V over 2. So we can sort of see the problem, and then to find the energy released for that bit of charge, well, I have to add up that strip, which is going to be half as big as the first strip that I calculated. Of course, eventually we're going to have to sum all of those strips for the whole graph. And in that way we can see that the energy that was stored on the capacitor, and therefore the work done on the charge as it's being released, is going to be the entire area under this graph. And so let's label that, and let's see then how we can evaluate that. So let's do a line up here. Well, we can see that the energy therefore stored on a capacitor is the area of that triangle. And can you see, so it's the area under the graph. It's a bit similar to, if you remember, Hooke's law and the energy stored on a spring. Quite very analogous. Well, the energy stored is going to be the area of the triangle, which, well, if we have plus Q, we know that Q is the initial charge stored at the right at the beginning. And so we can see that the height of the triangle is Q, the base of the triangle is V. So it's going to be a half Q times V. Great, we've done it. So we've solved the problem and we've found out how much energy is stored on a capacitor and how much energy we've got available for release. Well, there's a couple of other ways of writing that, because remember, because Q equals CV, then I can actually eliminate Q from this equation, and I've got an I could say it's a half, and I can say, well, Q is CV, so I've got a half times CV times V, so I get a half times CV squared, and then I've got another alternative. I mean, it's only got, I put the bars on here for that particular example where V was V, but of course in the general case, V is just the voltage that the capacitor is being charged to. And or alternatively, I could eliminate V, because V is Q over C, and so I could put V is Q over C there, and I get another expression which is a half Q squared over C. So I get Q squared over 2C. So I've actually got 3 expressions for energy stored on a capacitor. You do need to be able to know where all of those come from. So you need to know the graphical approach to find that, and of course how to derive these other ones from that original one using Q equals CV. So brilliant, so I hope that all makes sense. Well, let's just have a little quick look at that kind of last mystery, the fact that that of course the work we had to do by the battery to charge a capacitor is QV, because the battery supplies a potential difference or an EMF of V, and all the charge that goes through the battery is moved through that EMF. So the work done charging the capacitor is QV, but of course the energy stored is only a half QV. So the question then is, where did the other half of the energy go? Well, that's a good question. Well, it turns out that exactly half of the energy is dissipated in the circuit, because during that charging process, I mean, current is flowing, and so energy is dissipated in the resistance as current flows through there. And it turns out that it is exactly half. That's not obvious why that should be, but there we are. That is, and it's worth bearing in mind, because that is sometimes referred to in questions, the difference between how much work the battery's done and how much energy is stored on the capacitor. Great, okay, so try out 1 or 2 of the questions. It's very common that in a question you'll be asked to find the energy stored on a capacitor.